Hello, welcome to Picture Me Coding with Eric Gaker and Mike Mull. Hello, Mike.
Hey there.
Mike, last week we talked about Unix, the history of the Unix operating system, including its invention at Bell Labs, a little bit about Bell Labs. We didn't get to finish our discussion, and I was really eager to get to a question that I have that I want to unpack with you, which is, why was this thing so successful?
I think it was mostly the cool name.
I got a funny, sort of naive, this is just my childlike mind. So a eunuch, Eunuch, look it up if you don't know what it is. It never occurred to me that Unix, the operating system, ever sounded anything like this other word, eunuch, pluralized, until I read Brian Kernighan's book. It never occurred to me that that was a joke that exists. I'd never heard anybody make this joke. I'm just a child in the world. I had no clue. Was that like a thing that people would talk about when you talk about Unix?
I don't think it was widely discussed. There was this sort of semi-famous cartoon that came out. I don't know, it's probably in the 1980s about, this guy who grossly misinterprets what the conference session is about. And it's kind of a joke about Unix and Unix. But people had obviously got the joke.
It didn't seem like they were thinking of that when they named it Unix, but maybe I wouldn't put it past them to slip a joke in there with the personalities that you read about in Brian Kernighan's book. Last week, Mike, we talked about the timeline, the cost, and the effort to build this. We started talking about what made it original, what was unusual about it. They use that word unusual a lot in the Dennis Ritchie, Ken Thompson paper. And just to recap, the materials that we read to have this discussion today, there were really three things that we looked at two that we looked at in detail. One we just kind of took some pieces from. The first is a paper published in the ACM by Dennis Ritchie and Ken Thompson, and that paper is called the Unix Time Sharing System. That was published in 1974. And then Mike and I read a book by Brian Kernighan, a much more recent book called Unix, a history and a memoir. Kernighan, of course, the Brian Kernighan famously of KNR, the C programming language book. We also have a little bit from John Lyons' annotated version 6 of Unix and his book, A Commentary on the Unix Operating System. So a little bit of notes from there to help us flesh out our understanding of Unix, primarily the 6th edition. So we had really kind of started talking about what made Unix interesting or unique last week. We talked about the file system. The most important job is to provide a file system, Ken Thompson writes. Everything is a file, including special device drivers and things. And we talked a little bit about the shell, a little bit about standard and standard error. But I wanted to go back because in the paper, the Ritchie and Thompson paper, they talk about the implementation of the file system. Not only is it the important job is to provide a file system, not only is everything a file, including standard in, standard out, but here are some notes about how the file system is actually built. And I thought this was kind of cool. How familiar are you with inodes, Mike? What would you put on your on a rainbow? Are you like a blue or purple? Maybe a yellow, red? What's your level of understanding of inodes?
I'm unclear if blue is good or bad.
Oh, once you picked a color, I was going to assign it more knowledge than I had.
Okay. I know what the term means. I know that they're associated with files. I think that the practical way that I have tended to use them over the years is to determine if two files are the same file. Yeah. If you have like a symlink or something and you want to figure out it actually points to a particular file, you can look at the inodes.
Yeah, that's more knowledge than I have. So you're like a green. I'm more like a purple, a little bit more vague. I know they have something to do with files, but I kind of always forget the definition. There's a handy definition on page 362 of our Ideas That Created the Future book. Thompson and Ritchie write, a directory entry contains only the name for the associated file and a pointer to the file itself. This pointer is an integer called the I number for the index number. When the file is accessed, the I number is used as an index into a table, the I list. The entry in that table is the I node. And the I node contains the description of the file as follows. And then he enumerates 9 different things that you can get in this I node entry. Number 1, the owner. Number 2, its protection bits. What do you think that means? Chmod stuff?
Yes.
Okay.
Yeah.
Read, write, execute, user group, world.
That's my interpretation of what that means, yeah.
Okay, so owner, protection bits, the physical disk or tape, as Erik snickers hearing the word tape addresses for the file contents, its size, part of the inode, the time of last modification, the number of links to the file, that is the number of times it appears in a directory. Now, I didn't remember that was on the inode, but that's actually pretty cool, pretty handy, because you can imagine a garbage collection system, and they go on to describe that. As soon as the number of links to a file drops to 0, you could throw that thing away, right? You can recover that.
It's a surprisingly sophisticated and sort of prescient design for the file system for the time.
I had that response too, like, wow, cool. They really thought through all this. They produced a pretty good answer. Last three are a bit indicating whether the file is a directory. You can see that when you do LSL. You've got that D guy there at the beginning. A bit indicating whether the file is a special file. What the hell is that? And a bit indicating whether the file is, quote, large or small. Do you know what special file means?
I think they mean devices.
Oh, okay. Okay, right. Because that's right. Because the quote from before, special files constitute the most unusual feature of the Unix file system. Each I/O device supported by Unix is associated with at least one such file. Okay, cool. So yeah, you can write to that thing or you can read from it, but it's special. And then also large or small. Does that still exist in the inode, do you think? I think that used to exist. I remember something about dealing with large files.
My guess is it still exists, but I was not familiar with it.
I couldn't remember if that was related, but there's some good stuff in there. And as we think about the contributions of the Unix operating system, it's hard for me to remember. I made this point a lot last week. It's hard for me to imagine a world in which this doesn't exist.
It is so embedded in how we think about computers, even in popular culture. The files is sort of like and it's been used literally as a joke in movies. Yeah, it's just such a common metaphor. It's hard to imagine now what it was like before the hierarchical file system.
Yeah, even in Jurassic Park, the character who saves the day, what's her name? Brian Kernigan talked about her in the book. He's like, yeah, you see references to Unix all over the place, even in Jurassic Park, where she says, I know this, it's a Unix system. And she's able to get in there and trigger the locks and save them all from getting eaten by dinosaurs.
Yeah, I remember that scene there. It's on a Silicon Graphics workstation, and there was this program that Silicon Graphics had released, and I can't remember what they called it now, but it would give you this 3-dimensional view of the file system.
Really?
Yeah, so that I remember they show that in the movie, and it kind of shows the files as like this, almost like a 3-dimensional cityscape or something. If like a big file is like a taller building than a smaller file, that kind of thing.
Have you ever had a day at work as good as the day that character of that movie had when she saved everybody's lives by navigating a Unix file system?
No, but to be fair, I have never worked in an environment with dinosaurs. So,
oh, okay. Yeah.
I mean, that seems like an unfair advantage.
We had managers like that, though, in the past.
Velociraptor managers?
Yeah, if you could trigger the door locks to keep those managers from coming into your building, you're golden. You saved everybody's lives. Okay, moving on. So there is the next section after implementing the file systems called processes and images. And processes makes a ton of sense. I use that term all the time. We talked a little bit about forking last week. I got a little hazy on the details with forking. One of my favorite things they talk about in the paper and Brian Kernigan's book is pipes. But before we get to that, I want to ask you to help me understand the difference between an image and a process. I was a little confused. I'm going to give you a couple quotes from the book. This is from the Ritchie and Thompson 1974 paper. An image is a computer execution environment. It includes a core image, general register values, status of open files, current directory, and the like. An image is the current state of a pseudo computer. Now, I've only ever heard the term image used back when I would create Linux ISOs. I've burned them onto CDs in order to boot a new instance of Linux to install it on a machine. That's not what they're talking about. They say a process is the execution of the image. Have you heard this terminology before, image?
A little bit. And I don't really know though how this differs from operating systems before it. So I believe they're implying that this is an innovation, but
Yeah.
I don't know what it was like in other operating systems before this, how programs were loaded and executed.
But you don't remember people using this term image, right? To talk about running programs or a state of the pseudo machine before you run the program. Like, that's not a word you've really heard, right?
I don't think it's a term that people use commonly. I think sometimes people like maybe will talk about it in terms of a program core dumping, you
Mm-hmm.
know, because you're getting basically a snapshot of the current state of the program. Yeah, it's not a term that, to my knowledge, is as frequently used as the term process is.
So you hear image, it doesn't immediately evoke some specific thing in your mind. Because to me, I'm like, what? What is this term? Maybe there's a different term.
So I guess I sort of think of it as being the state of a particular program at an instant in time. He uses this term at the end of that sentence. An image is the current state of a pseudo computer.
Yeah.
So what I think he's getting at there is that, this is not necessarily something which is actually in the computer's memory, or in the values are not necessarily in the registers, but it's got all the data necessary to put that stuff into memory and to start execution of the process.
Like a
So
snapshot? Like if you snapshotted the state of an operating system right before you load a process?
it's kind of the layout, I think. So I guess the thing that I would relate it to, that maybe people are a little bit more familiar with, is the format of an executable file on a modern like Linux system.
Mm-hmm.
So probably people may have heard of like the ELF format.
Mm-hmm.
So
Like
the
like from Lord of the Rings.
yes, yes, exactly. That's totally what it's like. Um, what does ELF stand for? ELF is
Extended something format. Linux format? No.
executable and linkable format.
It's not. I just made up some letters. I got
uh,
format right. If this were an interview, I failed that question, Mike.
so that file has information on how the program is laid out, in a sense. So like when you load a program, they talk about this later on in the same section, where they talk about the program is loaded into a virtual address space. And so there's this sort of, there's a segment that has the code, and there's a part that has the data that's static, and then there's sections of that where you can have heap allocations, and there's a section of that where the stack lives and can grow. And so the ELF file, or whatever the format is on your particular computer, sort of specifies how stuff is laid out in the memory of the computer when the program is loaded.
Okay. Okay. So let me just try to walk through it a little bit. Actually, here, let me start with the section you just talked about. So Thompson and Ritchie write the user core part of an image is divided into three logical segments. The program text segment begins at location 0 in the virtual address space. During execution, this segment is write protected, and a single copy of it is shared among all processes executing the same program. At the first 8K byte boundary above the program text segment in the virtual address space begins a non-shared writable data segment, the size of which may be extended by a system call. Starting at the highest address in the virtual address space is the stack segment, so it's the opposite side, which automatically grows downward.
Downward, yeah.
Yeah, so I load my program into memory. My program, let's say I write some Python program and I want to make some massive list of every website that exists on the internet. Well, Python puts everything on the heap. So the problem is, theoretically, if we didn't have an operating system to control this, my program is in memory and the data my program wants to operate on is in memory. And if the data my program operates on in memory grows so much that it overwrites my program, then suddenly all bets are off. And it's like in A Hitchhiker's Guide to the Galaxy, where they've got the improbability drive and they don't know why they land outside of a planet. They land somewhere because it's the most improbable thing that can happen. That's like what we're talking about, right? So they're saying you've got the program at the 0, and then there's a boundary where nothing can write over that program in memory. And then you've got a heap. And all the way at the other end of the virtual address space, you've got a stack.
That's still pretty much true on Unix systems now.
Did they invent that? They invented that?
Yeah, that's what I'm wondering. I mean, I don't know how much of this was novel to them and how much of it was borrowed from other ideas. I think the ideas of virtual memory were kind of around at this point in time in the early 70s,
Mm-hmm.
but I don't know how much of this was novel to Unix. It sounds like it was a lot of it was novel. I think the idea of so like when you're doing the fork system call, you're basically taking the image of the current program and making a copy of that. So I think that was novel. I think that was kind of a new way to
Mm-hmm.
start programs. I don't know how much these ideas in their essence were new with Unix.
It is just interesting that they have this idea of this. The image is we're going to like almost like a snapshot of what's in memory at the time that the program starts running, or at any point, maybe in the running of the program. So I think that is a pretty cool, concise description of loading a program into memory, making sure that it has addresses that it can write to for heap and a stack that it can write to as well. And it's weird to think that that idea was invented. That's a very dumb thing to say, but that's how I feel about it. Like, so that's in images and processes, and then they talk again about the shell. Not again, but about the shell. We talked a little bit about shell. Inside their discussion about shell, they say, look, we have these cool tools and utilities. We can redirect input and output. We've got globbing, so you can operate over a whole bunch of parameters at once, for example, like star syntax and stuff. We can background things. We can write shell scripts and run them because the shell itself is a command. Like running a shell can invoke other shells as children processes as well. They talk about pipes, and then later they come back to pipes because in the shell they're represented as filters. This is another terminology I was curious about. Have you heard people talk about pipes as filter? I've only ever heard pipes. Have you ever heard the term filter for a pipe?
Maybe less common today, but I have heard people use the term filter. We people would talk about that in the old days when you would run a command and pipe the output into grep or into word count or something like that. And you could chain those things together and people would I know that was kind of like the technique that they would use to do certain types of text processing,
This is an extraordinarily useful tool.
especially for the kinds of things that they were doing at the time, taking text and trying to format it in different ways and put it in columns and paginate it and stuff like that. So it was kind of I think the terminology sort of grew a little bit out of the application.
We tend to use the word pipes for this in Brian Kernighan's book, and in the Ritchie and Thompson paper. They call the actual like the typed version of a pipe, the vertical bar. They call that a filter, but we just call it pipes. For them, pipes are like the actual system call implementation, I think. Anyway, we just use the word pipes. But here's from the paper. They write, quote, an extension of the standard IO notation is used to direct output from one command to the input of another. A sequence of commands separated by vertical bars causes the shell to execute. This one gave me pause a little bit. It causes the shell to execute all commands simultaneously and to arrange the standard output of each command to be delivered to the standard input of the next command in the sequence. Now, tell me, am I getting a little too hung up on simultaneously? You can't do it simultaneously, right? Is there something magical? That's just maybe the word choice a little weird, right? He's really saying you do this, feed the output into the input of the next one.
The thing that I will do occasionally is I'll run something. I'll do a grep, and then I'll run that into word count to get counts of lines that it's matching or something like that.
I
And
do
so
that too.
what I think he's saying when he says that they run them simultaneously is that it's not a case of they're running grep, or yeah, it's not a case of them running grep and then shoving all the output into some temporary spot and then running word count and taking all that stuff that they shoved in and running it through word count. I think what they're saying is that they are literally like starting those two things up as processes and letting the output from one stream into the input of the other.
In the paper, when they're talking about, they call it filters, we're talking about pipes. They give this really painful example of how you would run a series of programs where each program uses the output of the previous one, and it looks awful. You'd have to take the output of every single program, feed it out to some temporary file you create, and then a new program to slurp up that temporary file and produce maybe another temporary out file. And it just struck me how I've done that sometimes when I want to see the intermediate stuff. That's cool. Or if I can't remember exactly the T, I always get confused with T. But
Yeah.
without pipes, you would have always had to do that. And it just was like, oh, wow. Can you imagine how horrible that world would have been if they didn't? Kernighan actually his history on this is so fascinating. He says that pipes are perhaps the single most striking invention in Unix. And I find that compelling. I find that like, yeah, I could buy that is one of the most fascinating, unusual things that shows up in Unix. He says, and this is a quote now from the book, Doug McElroy, that was the leader of their department, he had the idea first in a 1964 paper. He wanted to, quote, allow arbitrary connections in a sort of mesh of programs, but it was not obvious how to describe an unconstrained graph in a natural way. And that is different. I mean, that's like a graph, right? Like getting feedback on it. Is it a DAG? Anyway, he writes, Doug continued to nag and Ken continued to think, Ken Thompson. But then he goes on, Ken one day said, oh, one day I got this idea. And he adds the pipe system call to Unix in an hour. And he describes it as super trivial using input-output redirection that was already there in Unix. And so then he starts trying it out and he's like, the phrase was mind-blowing. He didn't know that this was going to be such a mind-blowing thing. And what ended up happening is they were so eager to use this once they realized how powerful it was that Brian Kernighan writes that Ken and Dennis upgraded every single command on the Unix system in a single night.
To be fair, there were probably a little bit fewer programs on Unix at that point in time than there are in 2026. But yeah, I guess we should probably also make clear too that the input and output redirection stuff was novel to Unix as far as we know.
Yeah, and we talked about it a little bit last week, but yeah, and then you could say, oh, if I can take input and output and send them anywhere, I can actually send one output into another input. Well, that's pretty cool. So they add the system call, the pipe system call, and then they add that bar syntax in the shell, which they call the filter. I don't remember ever grasping the idea of pipes. I remember reading my Linux book by I can never remember who wrote the book, but I know John Mad Dog Hall wrote a review of it. The pipe syntax, I don't think I immediately got it, but pretty quickly after I got it, I never really wanted to use input and output redirection again. I wanted to always pipe, and when I'm trying to pipe something and it doesn't quite work because I have to use like the alligator mouse, I get a little like, oh, what did I do wrong? The thing about pipes though is they're fundamentally, and here I'm going off on the philosophical tangent. Tell me if I'm out in space. That's function composition, is it not? That's category theory. That's like there's math foundationally in there. The reason it's such a powerful abstraction is it's a core component of combining things into bigger things. It's a core component of computing. No? What do you think? Function composition?
I believe it is function composition of a sort. And this was always presented to me from the first time that I started using Unix as being sort of not only the fundamental idea of Unix, but sort of like a fundamentally important computer science concept. Mm-hmm. So, this idea that you write small programs and you string them together was a much better way of doing things than trying to write big programs that do everything.
Oh, that's the Unix philosophy. So I want to talk about that, actually, the Unix philosophy. But just to wrap this up, so we were talking about what makes Unix novel. And there's a number of things. The file system, everything's a file, the special files, the inodes, the way in which processes are loaded, the way in which memory is laid out for programs, the shell, all the tools in the shell, pipes or filters, they call them. That's a lot of cool stuff. It's stuff that's become completely ubiquitous for us. I think we could look at the stuff and go, yeah, I use all of these shell tools. A lot of these tools, I use them every single day. It's not necessarily surprising that it would become popular if they have invented tooling which has such a wide utility that so many people can use. But at the same time, sometimes tools get invented and they're really useful and they don't get used. Like I want to talk about why why was it success? It was this weird. It was an operating system built by a phone company that you couldn't even run unless you went to a university, and they had a license for it.
There's some lines from, is it from the book or from the paper, where Kernighan basically talks about how, well, first thing, there's one thing that he says that I think it says in the paper, and it always kind of surprises me, where he says there was no real objective with Unix.
Yeah, that's the first thing I want to talk about. Yeah, that's in the paper. Thompson and Ritchie. Oh, I'll give you the quote. Perhaps paradoxically, sorry, this one makes me laugh. Perhaps paradoxically, the success of Unix is largely due to the fact that it was not designed to meet any predefined objectives.
Right.
That's funny.
I think this is an interesting idea, an interesting quote, because it's so contrary to the way that we think about making software. Almost all software methodologies now are built around this idea of, trying to nail down precisely what the humans want the software to do before you do anything.
Yeah, MVP, avoid second system, avoid kitchen sinking the thing, MVP. What do your customers want? Build that and no more.
Right. And then, there's even like a whole industry of specification for software, which, has its place. But it's just interesting to me that this incredibly popular and persistent thing was just really something that people were tinkering on.
Yeah.
And, wanted to solve problems that were interesting to them. They found reasons for getting funding for it, this idea of formatting patent applications and stuff like that. But they weren't really thinking, my goal here is to make a universal operating system for every computer that will ever be created.
Yeah. Yeah. I want to make it so people can have a computer in their doorbell. I read actually a book by Linus Torvalds. Linus Torvalds, the author of Linux, if you have not heard of him. And his book is called Just for Fun, The Story of an Accidental Revolutionary. I read this probably a decade ago. It was fun to read. I should see if I still have it on my bookshelf and read it again. But there's almost a similar motivation there. I just did this because it was interesting. It's just kind of shocking that somebody could pursue a technical project like this because it's interesting, because it solves a few of their problems, because it's fun to work on, and then boom, we've got something that everybody in the world's using. It's kind of not what you would predict.
Thompson and Ritchie also say in the paper that they are programmers and they were writing the operating system to make it easy for them to write programs.
Yeah.
And
yeah.
I
That's a good quote. Yeah.
I suppose one thing that we should probably throw into this discussion is that another thing that came out of Bell Labs, which is sort of integral to Unix, but also separate, is the C programming language.
Mm-hmm.
And, we talked about the Kernighan and Ritchie book in the last episode, but they built this programming language, which is, now sort of what Linux is written in at Bell Labs. And so you have to keep in mind that, these guys were writing assembly language before that. And so they were like they were writing Fortran and they were writing assembly language, but they were like fundamentally programmers. They were not even really what you would think of now as being a research computer scientist. They were really programmers.
I think that's why I find Brian Kernighan's book so relatable. I don't read it and think, oh, there's Richard Hamming and Claude Shannon and Ken Thompson. I mean, everybody talks about Ken Thompson as like the most amazing genius they ever met. But the way Kernighan describes these people, they seem like fun to hang out with. They seem like really fun to collaborate on programming problems with. They seem like coders, like you could just go and write stuff just for fun and solve programming problems and you've got people who are contributing novel graph algorithms. You had Kernighan working on a graph cut problem before they knew that was NP complete. They're doing hard stuff harder than I've ever had to do. but there's a real kind of they seem like hackers at heart, and I just completely completely sympathized and like wanted to be in the room with them the whole time I'm reading the book.
Yeah, they seem like interesting people too. So I think when you talk about them as being hackers, or if you like look up pictures of them from the 1970s, they look a little bit like pocket protector guys.
Yeah.
Um,
Yeah, they've all got these like thin beards.
right. But there's also a bit in the book about how a lot of them in this group 1127 took up flying.
Oh
So
yeah. Yeah, they
Ken
went to
Thompson,
Russia and flew in a MiG.
yeah,
Yeah.
a couple of the guys went to Russia and flew in MiGs, but several of them in the 1127 group became pilots, and they called it like the 1127 Air Force or something like that.
Yeah. So I want to go back to, so you mentioned the two quotes from the paper, which are really interesting. One, we didn't have any predefined objectives. That's why I was successful. Make sense of that, if you will. Two, we're programs. So we made the system as easy as possible to write, test, and run programs. Now that one makes sense to me. But Brian Kernighan gives a number of technical reasons for the success. You brought up C. He mentioned C. He says the C programming language is one reason why Unix was successful, and they kind of reinforced each other. C was also successful. He says one of C's novel contributions to programming languages was the way that it supported arithmetic operations on typed pointers. A pointer is a value to a corresponding address. He gives that description, right? So a pointer, you're pointing to a memory location, and there's a typed thing that's stored, resident in that memory. And so you can actually manipulate a pointer arithmetically, and you can cause all kinds of really cool bugs that way, right?
I don't know if this will even make sense to people who haven't done like assembly language, but the idea of pointing a register at a memory location is pretty basic there. But the idea in C that you could have a pointer to say like a 4-byte integer array, and that by incrementing that pointer you go to the next 4-byte integer instead of
in the array.
In the array.
Right. So you're looping in the array by doing pointer math.
Right. And that if you've done C, that's sort of like very integral to the language.
Mm-hmm. So Kernighan says that Ken Thompson actually tried converting Unix from assembly to C 3 times in 1973, but he found it too difficult. And Kernighan says he was able to do it after Dennis Ritchie added structs to C. And I was like, whoa, C didn't have structs. So then the 6th edition of the Unix kernel, the one that Lyons wrote about, the one that really gained widespread adoption outside of Bell Labs, it had about 9,000 lines of C. And Kernighan says C is one of the reasons for the success of Unix, and Unix is also part of the success of C. He just said there wasn't like a suitable language before that. So C was suitable for doing the work they wanted to do. He does also talk about some of the things we already talked about. The hierarchical file system was a major simplification of existing practice, he says. Though in hindsight, it seems utterly obvious. What else would you want? File names are the path from the root separated by slashes. And yeah, it definitely has this feeling of, now that you've pointed it out to me, all of this stuff seems so obvious, but it would have never occurred to me on my own.
It's interesting. I think that the way that people use Unix now is probably different than the way that Ken Thompson and Brian Kernighan and Dennis Ritchie envisioned it being used. I mean, people
What do
still
you mean by that?
Well, people still do use it for programming, obviously. But I think the idea of you use it not only as your programming environment, but that you use it to write the programs that you use on a daily basis for yourself is
run them. Yeah.
Yeah. I think, it's gotten to be now that Unix is mostly a server platform.
Yeah. I mean, Mike, let me ask you this question. Which system are you going to trust? Here's a proposed problem for you. You need a program that locks the door so you don't get eaten by dinosaurs. You going to trust a Unix system, or are you going to trust some other Windows server, my friend? I know what I'm going with.
What's that formally verified microkernel called?
Okay, Thompson wrote that trusting trust paper too, didn't he? That's a little bit off topic,
That's
but
that's right. Yeah, I think that was his. I think the trusting trust paper was Ken Thompson's Turing Award lecture.
I think
I
think you're totally right. Okay,
if you
so
haven't read that paper, we haven't talked about it on the show, but if you haven't read that paper, it's mind blowing and it's very short. So you should go. You should like stop the podcast right now and go read that.
or keep listening and read along. Do both. Multitask. Background task. Sorry. Okay. So Kernighan again, hierarchical file system, C programming language. The fact that files contain uninterpreted bytes, that's what made it successful. Again, hard to imagine a time before that. He says that files are created, written, read, and removed with a half dozen straightforward system calls so that the actual interface for doing file stuff is straightforward and not there's not like this Byzantine array of different commands you have to invoke to do different file things. And he would probably include in there this concept of the inode, which we talked about. And then, as we were saying with C, he says that a high level implementation language for user programs and the OS helped Unix take off. He said that other OSs tried this. Maybe he's thinking of PL1 and Multics there. But he says, and this is a quote, C was much more suitable than its predecessors. That's what the quote I was looking for. And it led to portability of the OS. Portability, why do you think that's important?
I think probably because there's more than one computer manufacturer.
You're saying we're not all running PDP-11s. I just thought you'd have more examples of like running Unix on other stuff and how or maybe other operating systems. Like because I don't have any direct feeling for that. For me, it's just I mean, I would install Linux on anything that I could, and I mean, I don't have anything really obscure to install it on.
Yeah, I mean, it's been adaptable to a lot of different hardware platforms, and it's been adaptable to high-end servers, but also embedded things. And it's got this structure where you can sort of add things that you need or exclude them if you don't need them. And some of that's evolved since this time, but now most of it's written in C, and so it's in a language where it can be ported to other hardware without huge difficulty.
Yeah, and I think what Kernighan's ultimately arguing there is that they built all this tooling around C to make it portable, to generate different machine code based on C, so you could target different architectures. Like they built all this stuff. They built Yak and Lex and Make, and this all came out of Bell Labs, and it was all to make their production of programs easier, for the writing of programs easier. But it actually led to C being very portable, and that portability led to Unix being really portable. That was kind of the argument that he made. So these are the technical reasons, but he also talks a lot about the culture. Now, you referenced the Unix philosophy, and I've heard people bring this up over the years, and I got to say, it's one of those things where it's sort of like I know it when I see it. Make each program do one thing well. You ever have those discussions at work? Like, let's follow the Unix philosophy. My program does one thing. It orders pizza and returns my library books. That's the type of discussions I have at work. And I'm like, wait, I don't think that's one thing. I think we're doing a lot of, should we do both? We can do both those things. I don't care. I'm not writing Unix, okay?
It is harder to define that one thing once you get past a certain level of complexity. Listing files, it's pretty easy to figure out what that means, although there are pretty many options on LS at this point in history. The idea that you have a program that lists the files in your file system is a pretty easy thing to encapsulate. And I don't know that everything that people want to do is that easy to put a circle around.
Here's my favorite example. Pandas, read CSV.
Because of the million different ways you can do it? Or
how many it has like the most arguments I've ever seen. How many arguments? Oh, 1, 2. Actually, it's gotten better. 5, 6, 7, 10, 12. Still counting. 4, 25, 26, 27. Still counting. I'm up in the 40s. 44, 5, 6, 7, 8, 9. About 50 arguments to pandas read CSV. Do one thing.
But it's very focused on reading CSVs.
It's right. It does one thing. It reads the CSV. Okay, so Kernighan says The success of Unix is partly due to some cultural things, including the Unix philosophy as laid out by Doug McElroy. McElroy, the guy who came up with the idea for pipes and who badgered Ken Thompson until he put them in there. and Kernighan says McElroy read all their stuff and made it beautiful. Like he was an incredible editor. So in 1978, Doug McElroy presented the Unix philosophy as three things. One, make each program do one thing well. Two, and this one's interesting, expect the output of every program to become the input to another as yet unknown program. And three, design and build software, even operating systems, to be tried early, ideally within weeks. Don't hesitate to throw away the clumsy parts and rebuild them. Now, I love these principles. They make a ton of sense. I would love to keep them in mind at all times. I'm curious, though, about the output of every program has to be the input to another as yet unknown program. That's a little weird.
I think the way that I would put that is there's this idea that I've tried to stick to over the years with marginal success, which is that you should write code with the expectation that other people will use it at some point. So make the interfaces clear, make the boundaries clear. Don't have like weird pathways that do unexpected things. Don't surprise people. I think maybe that's what he's getting at.
You threw in so many things in there, and my mind just spiraled in all kinds of directions. And all I was thinking, I mean, that last thing there was like the Haskell don't launch the missiles thing. All I was thinking is write every program as if the output will be piped to another program, and that other program may not exist yet. And I'm like, whoa, that's cool. That's a cool thing to shoot for as an ideal. But if the program's not written yet, how do I do that? And what you're saying, I think, is be consistent in your output. Okay, I'll try to do that. Kernighan also has some other Bell Labs cultural practices he refers to, and I'm going to point to 6 of these that Kernighan brings up, of the ones he brings up. These are cultural practices. He says we were very collegial, and you get that by reading the book. And he quotes Doug McElroy, that's the guy we were just talking about, the Unix philosophy. Doug McElroy says, collegiality was the genius of the system. Nobody's advancement depended on the relationship with just one boss. So it's kind of cool. Like you're not doing work in order for career advancement. It's collegial. You're all like lifting each other up. You can go and just help somebody work on their program and you're benefiting the organization and you don't have to worry that your contributions aren't being recognized, when it comes time to performance reviews or something like that. And similarly, Kernighan says that Bell Labs is a very stable environment. Money, resources, mission, structure, no thrashing. They got a huge, ample amounts of time and not a lot of direction. It was just like, just go build stuff, go figure things out. That's how it seems from his book. I mean, that's a pretty rad working environment, no?
Yeah, it sounds fun. It sounds like one of those places where your compensation and your career advancement would be a sort of a secondary concern. He talks in there about like I think they called it the Unix room or something like that. So most people at Bell Labs had their own offices, which I think is also a good idea. But they had this one particular room, which was kind of like where they put the computers and everybody went in there to hack on Unix stuff. And a lot of people just hung out there all the time. And it just sounds like an environment that would be almost addictive, like almost potentially, distracting from normal life a little bit.
This seems like the type of environment you and I would just absolutely love to be in. I mean, we've had work environments. Part of the reason we get along well is we've had collegial workplaces that were sort of briefly like this, but nothing like the tenure and the success of Bell Labs. And also, there's a Dick Hamming quote that he gives that he says another aspect of the success of Unix is that we had a problem-rich environment. And he quotes Richard Hamming saying, quote, "If you don't work on important problems, it's unlikely that you'll do important work." That's a pithy statement. I got to tell you, though, when I read it, I thought, ouch.
Yeah, I saw Hamming give this talk at University of California, San Diego back in like the 90s or maybe late 80s. And I had the same sort of reaction. A lot of the stuff he says in there is, you have to work on important problems and you may have to sacrifice certain other aspects of your life to work on those things and focus on those things. And I came away with it thinking, yeah, I'm probably not going to do that. So,
So, bye bye, important work. I'll just keep doing my thing. I had friends back at college who had studied graphic design, and then they went and they like designed direct mail. I knew this one guy who was designing socks that were like SpongeBob. Like he was like they did all the SpongeBob stuff, so he would like Photoshop all day long SpongeBob and Patrick onto socks and apparel, and he just absolutely hated it. Hated it so much. He hated that job. That was probably not important work.
I knew this guy who he graduated from the MIT Media Lab. He was a really cool guy, and I thought he was going to do exceptionally interesting stuff. And then I lost touch with him and looked him up like 20 years later, and he was like the VP at a bank or something like that.
Oh,
And probably interesting work, probably maybe satisfying, but I just sort of felt disappointed. So
hope he's not listening. The last one that Kernighan, and actually I have another one, but this is not one that Kernighan raises. I just wanted to throw it in there at the end. But Kernighan says another aspect to the success of Bell Labs culture was that they had technical managers. He writes, the managers have to understand the work they manage. This one's a little more controversial. I think you are a fan of this. I'm a little bit more agnostic. Do you have to have technical managers? I feel like I've seen the existence of successful managers who aren't necessarily technical, but I have also had non-technical managers I chafed against and constantly was like, stay in your lane. You're giving me suggestions that don't make sense. Leave me alone.
I think I am sort of an extreme opinion on this.
You got the hottest of takes.
So I think there probably have been successful managers who were not especially technical, but I think they run more in the vein of project managers, people who sort of like facilitate and run blocking for you. I think I agree with Kernighan that you need people. I think you need people who like wish they were doing your job.
To be your manager. They're envious of you.
I really do think that makes for a better technical environment, but I realize that is not a majority opinion in the world.
So one thing I noticed in Kernighan's book too, which also makes it fun to read, is there is this subversive office personnel thing happening. Like Thompson, Ritchie, Kernighan, and others, they have a lot of fun at work, not necessarily in the spirit of what work wants them to do. So there's a number of different examples, like even the whole, hey, we need a new PDP 11 to do the OS, but the company says we don't do operating systems, so we'll just go and hijack the patent system one and do our operating system work on their thing, and we'll also write them some programs so they could do their dumb patent applications. Like there's something subversive about this. Like, yeah, I'll do some stuff you want me to do, but I 8 hours a day, 7.5 hours, I'm doing what I want to do. Okay, that's why I'm here.
Yeah, I liked how like Kernighan had at some point Bell Labs made people get badges, and
that was my other example. Yeah,
Kernighan got a badge with Mickey Mouse on it. And
yeah, they were supposed to have a badge with their faces on it, and everybody was like pissed off about this. Like, I don't need a badge. Why you might have a badge? They made a badge for a gremlin from the movie Gremlins, and I had a funny gremlin picture on it. And it was like, I can't remember, it was G Remlin, and it just said Gremlin on the badge. And he was like, yeah, nobody ever noticed. They also had that. I like the one with the Vortex machine, which was it was like a speech synthesizer program. And so Doug McElroy writes this program to take English phonemes and get them. He writes a program called Speak. And so you could type in speak and then a quote, and then the voice synthesizer would say it. And so every day at 1, their lab would say, lunchtime, 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 yummy, yummy, yummy. And it's because the cafeteria would close at 1:15. Like, these guys they're kind of rebels a little bit,
I like the one about how like some guy accidentally left his portrait in a bathroom.
Peter Weinberger, like he was their department head for a while. Yeah.
Yeah. And they took his picture and they like mixed it with the AT&T Death Star logo, and
they put it everywhere.
Yeah. The culmination of that was that somebody painted it on the side of a water tower.
Yeah. And you get this. Yeah.
I just think that's, that's next level stuff right
That's
there.
next level. Yeah, and you get the idea that Kernighan probably knows who did that, if not him, but he's not going to say. even
If he
at this
wasn't
late
involved,
stage.
he definitely knows who did it. So
Yeah. I really liked reading this stuff. It was just absolutely a huge pleasure to read Kernighan's book. And if you're like us listening to this, if you're enjoying these stories, I mean, we've covered a lot of stuff in the book, so hopefully we didn't totally give away the ending. But I recommend go out and read Kernighan's book. Read the Thompson and Ritchie paper. It's totally readable. It's a good read. I think I will continue to struggle to put my head in that moment in time where Unix emerges, and it is so different from what comes before. But it's really fun to try to do that.
I don't think there's even really any education about that stuff anymore, like pre Unix operating systems. I think I was involved in one company in the early part of my career that had some IBM mainframes, and there were people who had to write so-called job control language or JCL scripts to submit programs. I sort of saw the tail end of that, but it was nothing that I ever really had to work with myself.
I guess I think it will give me a new appreciation for the tools that I use on a day-to-day basis where I'm like typing cat. Like, oh yeah, that was invented in the 70s and I'm still typing cat. And yeah, it was kind of reinvented by the Richard Stallman crew, the GNU people, as they're like, and the BSD people. They're reinventing this. They're rewriting this stuff, but it was invented there at Bell Labs in the 70s, and I'm still typing the same command. Grep, I'm still typing that same command, although I tend to use ripgrep. I'm a big ripgrep fan. Use ripgrep if you haven't used it. It's cool stuff, Mike.
It says to me that they had a good sense of what was important. And I think that comes from the fact that they were programmers, and 50 years later, we are also programmers using tools for programmers.
Yeah. I guess I wonder if typing text into a terminal, like I'm surprised we're still doing that. But then as I reflect on my own work, I can't imagine ever creating a thing that that would have an impact as massive as they had with this stuff that they had, that they just dreamed up at work to solve their own programming problems that they had a lot of fun making. It's just astounding that it's gone as far as it has.
It does seem like it's unlikely that things that simple will turn out to be that important and persistent.
Now, listeners, if you'd like to reach us, feel free. Podcast at picturemecoding.com. We also have a Blue Sky account, Picture Me Coding. And we also have a Patreon. If you'd like to support the show, Picture Me Coding. My name is Erik Aker. My co-host, Mike Mull. We will see you again in a couple weeks.
See you next time.
Bye-bye.